Okay, hello everyone. I'm Yizhuang You. First of all, very happy to be here. Thanks for the organizers for inviting me. So today I want to talk about can large language model learn to speak the quantum language. So large language models are generative models which learns the joint probability distributions of sequences. I guess we are all using it in our daily life nowadays. And by the quantum language, I really mean the measurement outcomes that people collected from these quantum devices or quantum platforms. So the question is whether we can use a language model to learn all these measurement outcomes collected. So this is in the background of we are entering an era of maybe we can call it quantum big data, where these quantum processors are able to produce massive collections of measurement outcomes. So these measurement data are the language that nature tries to speak to us because nature runs in a quantum mechanical way fundamentally. And then we want to learn from these native speakers, which are the quantum device, try to learn fine structures of quantum mechanics, quantum many-body physics. So measurement plays the central role in the discussion. It serves as both as a way to read out information from the quantum system to your classical processors, and it also serves a way actually to control quantum systems if you can design measurements process. So people have been talking about using measurement to prepare quantum states. So that actually leads to a lot of new opportunities. And that is very different from the conventional way of learning quantum many-body physics. Conventional way of learning is like you start from some initial state through a deterministic state preparation process. You prepare some quantum many-body system, and suppose you can prepare the identical state repeatedly, then one can perform measurements on repeated copies of states to study the property of the state. But now we have these new ideas, or people develop this new paradigm of trying to insert measurement during the state preparation process. And then now the state that you prepared will be conditioned on the measurement outcomes. And the measurement outcome will be sampled from the Boring distribution, follow the rules of quantum mechanics. So very likely you are not going to see the same measurement outcome for the second time in your experiment. So it will be very challenging to study the physical property of the final state that is prepared by the measurement, or so-called measurement-induced state. One very sample costly version to a high sample complexity version to study that is a post-selection. You can maybe try to post-select on the measurement outcome and maybe study those states. So I want to say this post-selection is not only a problem for quantum measurement or measurement-induced states, it also exists in human language, because the way that we communicate with each other, say, how are you? I'm fine, thank you. The way that you respond to other people's language is basically you need to condition on what people said and make a response. So when I was young trying to learn English, there's a book called English 900 Sentences, which collects samples, right? And then what you do is, how are you? And you go to the book and then post-select out the sentence and then return with these results, right? So this book lookup is actually a post-selection strategy to speak a language. But we know that it's a very dumb strategy. And then that means post-selection is not the best way to process your data. Your data is this book. You should use the brain. We should use our brain to first learn this book. Because because in the language, these tokens are highly correlated. So that means the complexity is not so high as you think. There's a lot of correlations. If you make use of this correlation, you can reduce the data complexity, and maybe you can learn to speak the language. So a good language model, either human language model or AI language model, should respond to diverse prompts without the need of post-selection. So that means if we collect data like this English 900 sentence book, that's our data that can collect from experiment. We should use probably a learning algorithm first to learn the data distribution, and then maybe we can get more from this learning algorithm. We can generate new samples, even that is not appearing in your data. So that's the motivation for this collaboration. We try to use this learning approach to learn measurement outcomes, and then try to probe measurement-induced entanglement in a quantum many-body system. So the work is in collaboration with Google Quantum AI team, and also my student Wanda, and then Sam and Ahud from Berkeley. It's also supported by a few other funds. So in this work, what we try to do, we did two experiments, and one is a one-dimensional warm-up experiment. Let me first describe that. So it's trying to see whether we can detect measurement-induced or measurement-based entanglement or teleportation. So this is a very simple protocol that you start from the all-zero state using these gates to prepare EPR pairs, Bell pairs. And then that entangles these qubits together. And then you further perform Bell measurements between on the alternative pairs of qubits. So these measurements will basically project these qubits to entangled states as well. So in the end, the effect is that through the state preparation, through this unitary and then measurement, we are trying to establish entanglement that teleportates all the way from the first qubit to the last qubit, because all the middle qubit gets measured out. So this is a protocol that you can prepare entanglement across a far distance in order 1 depth circuit with the help of measurement. However, the specific entangled states that you can prepare out of this between the remaining unmeasured qubit A and B actually depends on all these measurement outcomes for the intermediate qubits. It turns out that according to this preparation scheme, that this A and B will enter one of the 4 EPR pair states, which is a stabilizer state stabilized by XA times XB and ZA times ZB. The stabilizer value, XA times XB, will be plus minus 1, depending on the product of all the measurement outcome, which is supposed to be also plus minus 1, across all the even sites, across, let's say, all the odd sites. So you need to product them together. And then for all the even measurement outcome, if you product them together, that gives you the ZZ correlation or the ZZ stabilizer value. So in order to determine which EPR pair states we are preparing, we actually need to it's conditional on the measurement outcome. If we forget about the measurement outcome, we don't condition on the measurement outcome, then we'll be almost uniformly mixing all the 4 EPR pair states, and then A and B will not have any entanglement between them. So the idea is that because in this kind of experiment, if you run it once, each time you will obtain a sequence of these preparation measurement outcomes, and then you only get one chance to make a measurement on A and B. You can't prepare A and B repeatedly. It's unlikely that this measurement outcome will appear again. So the idea is that you use this single chance, single snapshot to perform a shadow measurement on A and B. Although a single shadow snapshot was not sufficient to reconstruct the state, but the hope is that if you can collect these kind of data from experiments, then the data looks like all these preparation measurement outcomes combined with a single shot classical shadow measurement outcomes, and then they can be sent to a language model, and the language model is good at learning how to respond to a prompt. So you treat the preparation measurement as a prompt, and then try to predict what should be the response, which is the classical shadows. So if that learning is successful, then you can probably keep prompting your language model with the same preparation measurement outcome, although you only get a few chances to measure it in the experiment, but the language model can amplify this data and give you a lot of classical shadow that will enable you to reconstruct the state. So that's roughly the idea. So specifically, we basically build a transformer-based model, which is actually the architecture that people use in nowadays language models. The details is not so important. The point is that you put all these preparation measurement outcome as input, and then this transformer model will basically mutually attend each input with each other, passing information in a very complicated way, and you need to train that. The outcome eventually is a model predicted reduced density matrix A and B on the two unmeasured qubits, condition on all the preparation measurement outcome. So I put a C here because I want to indicate it's not the true quantum density matrix, it's a classical machine's prediction. So it's a classical prediction of this density matrix. On the other hand, because in the data set, for each measurement record of the preparation measurement outcome, we also collect a single snapshot of classical shadows. So from those single snapshot of measurement in AB, we can construct the so-called shadow snapshot state, and then we can try to minimize this loss function. This loss function is nothing but the negative log likelihood of observing this classical shadow condition on this machine's prediction. So if you try to minimize the negative log likelihood, meaning that you try to improve the likelihoods that you see, so your machine is trained to produce a good estimation of this reduced density matrix such that you have a large likelihood to reproduce the data that you collected from the shadow measurement. So that is how we can train a language model to learn to speak this quantum language. So after training, what we get is essentially a classical algorithm or a model that serves as a classical decoder that can perform a task which is conditioned on the preparation measurement outcome, which is all this intermediate outcome, and give an estimation of what is the reduced density matrix on the unmeasured state. Okay, so that is one possibility to build a classical decoder that is a learning approach. There's also maybe other approach we can benchmark with. For example, there's also rule-based approach, which you can try to predict this. Because in this task, it's very simple. We already know all these details. It's a simple EPR pair teleportation task. So we know that eventually A and B will be in one of the 4 Bell states, and then the 4 Bell states are classified by the product of all these measurement outcomes, so you can do direct post-selection. I want to say that it is possible in this case, but it is post-selection is not always possible in general case. So in this case, it's because the rules is simple, so you can use this rule to do a rule-based post-selection. You can also run a simulation to actually simulate what is A and B conditioned on all these measurement outcome. However, in the simulation, maybe you don't have the full knowledge about the noise model. So maybe your simulated result, your prediction may not be a very good estimation of the reduced density matrix compared to the experimental reality. So there are 3 different approaches: rule-based, simulation-based, and learning-based. And we will see which one works better. So after training, essentially, we want to get this classical decoder. So with a classical decoder at hand, no matter which approach you use, the goal is to perform certain decoding task, which is try to decode or try to understand how much entanglement has been induced between the unmeasured qubit A and B conditioned on all the intermediate measurement outcomes. So there are several quantities that can quantify information theoretical quantities which quantify entanglements or entropy. I will talk about them one by one. So the first quantity we are interested in is the von Neumann entropy of the subsystem A and B conditioned on the measurement outcome. So you use the measurement, preparation measurement to collapse the system to the remaining A and B subsystem, and you can quantify its entropy in this way. This entropy quantifies the uncertainty in this reduced density matrix. So ideally, if I'm running everything in my classical computer as a simulation, you start from a pure state, perform a projective measurement, then A and B should remain pure, and pure state doesn't have entropy, so entropy should be 0. But if you collect data from experimental device, then in reality, because of decoherence, measurement error, and all kinds of noise sources, then there is some uncertainty related to the state A and B if given the measurement outcome. But try to estimate the ensemble average of this entropy average over all the possible all measurement outcomes. This is not directly observable because this quantity itself is not linear in the density matrix, so you can't simply perform the averaging by taking samples and do the statistics simply. So that there's post-selection problem associated with that. So the idea to overcome or to solve this problem is to look at another quantity which is different from what we want to measure as the entropy, but as a quantum classical cross version of the von Neumann entropy. Well, in this expression, you still keep this rho AB, but you replace the other rho AB with this logarithmic in the front as your classical model's prediction. So the classical model can either be rule-based or maybe simulation or maybe learned. So no matter which one you consider, one can prove that this quantum classical cross entropy will be an upper bound of the ground truth entropy. So in this way, we can try to give an estimation of the entropy. And in order to calculate or to experimentally probe this quantum classical entropy, we can further use classical shadow data to replace this rho AB by their classical shadow estimation, such that the idea is that we first use some amount of training data to train our model and to get a classical decoder. Then we collect new data, which is like testing data. These new data will provide classical shadows and then also provide measurement outcomes. From measurement outcome, we can perform classical predictions, and then we put device collected classical shadows and classical computers prediction together in order to compute this quantum classical cross entropy. So this entropy actually, as I said, it's an upper bound. This quantity is an upper bound of the intrinsic uncertainty, intrinsic entropy in the system. So the gap between what we estimate as quantum classical cross version, this gap is actually a KL divergence between the model predicted density matrix and the ground truth density matrix. So it also serves as a very good measure to quantify how well the learning goes. So this is the experimental result. So the experiment was performed on a line of qubits all the way to, I think, 34 qubits, and then performing this teleportation experiment. And then we use the data to train our model. Then that is this transformer. This is a blue line. This vertical axis is the quantum classical cross entropy estimation. So it serves as the upper bound of the ground truth entropy. So we can also do rule-based post-selection, which is the green line. And there's also noiseless simulation, which is this red line. So you can see that the noiseless simulation is actually even worse than simulation is worse than learning. Learning and this post-selection, in this case, almost coincide with each other, which means that learning directly from the data actually provides a better estimation of the underlying density matrix. Well, the simulation, the reason that simulation is not good is because in our simulation, we haven't taken into account noise effect. Okay, so the learning actually was performed on like 8 times 10 to the 5 samples, which is actually much less than 2 to the power 32. In the largest system that we study, which has 34 qubits, all the intermediate measurement is on 32 different qubits. So potentially there can be so many possible measurement outcomes. So definitely this amount of sample complexity is not sufficient to perform any post-selection, naive post-selection. But since this problem is simple, we know that the post-selection, you only need to post-selection, only need to classify these data into 4 different classes. So that's why this task can possibly be performed using such a small data sample complexity or such a small amount of sample, far less than the amounts which you naively think you need to post-select. Well, but this entropy quantity doesn't directly tells you whether A and B are entangled with each other. So we can also look at other quantities like coherent information and entanglement negativity, which are defined in this way to quantify the amount of entanglement. Details is maybe not important. The point is that these quantities are entanglement weakness. If these quantities are positive, this positive value will testify the quantum entanglement. However, all these quantities are nonlinear quantities in density matrix, so they again have post-selection problems. So again, it's the same trick, just use the quantum classical versions of whatever coherent information or negativity. One can prove there are certain bounds. For example, these quantum classical cross versions are always lower bounds of the ground truth. So that means even if we have a very crappy learning algorithm, the algorithm learns very badly. It just makes the bounds looser. But as long as our algorithm learns something and then and we can use our learned classical decoder combined with the quantum data to estimate the quantum classical cross, for example, this curve is the cross negativity, and then a positive signal in your predicted this cross negativity will already mean that the true negativity will be even higher than this curve. So as long as this curve is above 0, that is actually a demonstration or proof of entanglement between A and B induced by all the intermediate measurement across a chain of 34 qubits. We can see, of course, if you go to larger system size, due to noise and decoherence, the amount of entanglement is decreasing between A and B. It's not perfect, but we can actually try to testify this entanglement all the way to 34 qubits. Okay, so far we see that using this learning approach, and in this study, it seems that there's no key advantage of learning because it's rather simple, but there are also very challenging tasks where we really don't know how to do post-selection. So we really need to rely on learning-based methods in order to build a classical decoder. For example, and we also want to ask a question, is learning always possible? Maybe there's also limitations of learning. There may be some cases, actually we should believe there must be cases where a classical machine cannot learn all the features of quantum dynamics. Otherwise, what's the point of building a quantum computer, right? If you can train a foundational AI model to learn the behavior of quantum computer in all possible cases, then we don't need to build quantum computer anymore. So this leads to this topic of measurement-induced phase transition, which is proposed in many previous works. And then studied by a lot of people here, and then it's a circuit where it's a quantum dynamics, it's a mixture of unitary and measurements. So you perform unitary and maybe weak measurement or measurement in a hybrid manner. So this kind of quantum dynamics can lead to two different phases in the steady state, the area law entangled phase versus the volume law phase. And it is believed that MIPT can also be viewed as a learnability transition that is about how much you can learn from all these intermediate measurement outcomes about, for example, the initial state or about the final state, doesn't matter. So in the area law phase, because you are measuring the system in a very high frequency, high measurement rate, so you are extracting information very effectively, and then this measurement outcome can tell you a lot about the quantum system. But in the volume law phase, that means there's some information that is hiding inside the circuit that never gets measured or easily measured out by your measurement. So your measurement will be very ineffective in predicting, for example, the initial or final state. So yeah, so that is so we decided to perform this kind of experiment on Google's quantum device with, instead of doing a 1 + 1D time evolution, we can consider a 2D cluster state. This is the idea of a measurement-based quantum computation, that you don't need to insert measurement during the dynamics. That's probably challenging. Instead, you consider mapping this 1 + 1D dynamics into a 2D state and then perform measurement everywhere in most of the systems, and leaving only 2 qubits unmeasured. And we want to ask whether these 2 qubits, you should think of them as the 2 qubits in the final state, and whether they are entangled or not. So in the area law phase, these qubits, which are far apart from each other, will have negligible entanglement among them, between them. But if you are in the volume law phase, then it can induce a lot of entanglement between A and B. So if one perform a numerical simulation, and there I need to say there's a parameter that can be tuned. So here the measurement is not in the z basis. Instead, it's in the z basis. It's in an axis that is tilted from the z basis by angle theta. So theta is the tuning parameter. It turns out if theta is 0, we are measuring in the z basis. And if you start from a cluster state measuring in the z basis, you will entangle everything. So A and B will have no entanglement among them. And then if your theta is like a pi over 2, then that's measuring in the xy basis. So a cluster state being measured in the xy basis is like a unitary evolution, effectively. So that will build up a lot of entanglement between the qubit A and B. So one can see a crossing indicating an entanglement transition somewhere at the critical theta value. So we basically use, perform the experiment on a 6x6 array, and then with the training sample, which is far less than the total possible of measurement outcomes, it only contributes as 0.46% of all the possible measurement outcomes. So definitely not sufficient to do post-election there. And then one can use this kind of sample collected from the experiment, which contains all the measurement outcomes as well as the classical one shot of classical shadow measurements to train a classical predictor, which predict the classical estimation of the density matrix, and then using the shadow and the classical prediction to calculate all these quantum classical cross quantities. For example, one can again consider the quantum classical cross entropy, which actually quantifies how well your model learns. There will be intrinsic entropy associated with the noise, but the model is trying to close this gap as much as possible. So you can see that with different theta angle values, this is in the area law phase, this is in the volume law phase. In the area law phase, there's almost nothing to, at the beginning, it's very easy, not too much to learn. And then gradually the learning tasks become harder, but we can still see that this model is trying to learn something. Horizontal axis is our training time, and vertical axis is this entropy. But in the volume law phase, model just failed to learn, so the loss function doesn't decay. So one can go to the final training epoch and look at how this quantum classical cross entropy varies with the measurement basis angle. So this left-hand side is the area law phase. So in the area law phase, our neural network approach, learning approach, can outperform the gate-based simulation, which because the gate-based simulation doesn't take into account noise effect. So it's not as good as learning directly from data. However, this task is quite challenging if theta is larger as you approach the volume law phase. Then at the point, the AI model will perform poorer than this simulator. And then this picture shows the amount of KL divergence drop during the learning process. We can see that AI puts a lot of effort trying to learn as theta increases. So this is the amount of information that gets learned by the AI. But up to a certain point, AI cannot learn further. So in the volume law phase, although there's still a lot of structured information, maybe there are still a lot of correlations there, but the correlation is too complicated that learning is very inefficient. Okay, yeah, almost there. So eventually we can use our trained model to predict, to quantify this quantum classical cross negativity, which quantifies the amount of entanglement between A and B conditioned on the measurement outcomes. So the red curve is the learning approach. It gives us, and the blue curve is the gate-based simulation, which means that in the simulation, either approach is a lower bound of the true negativity. But the fact that the gate-based simulation already predict negativity like that means that there's indeed entanglement between A and B. But this entanglement in the volume law phase is very difficult to be picked up by the learning algorithm. So the learning algorithm can follow this curve at the beginning in the area law phase where things are learnable and then fails even before it touches the MIPT transition. So there are many related work using either XEB, which is talking about how measurement outcome distribution is how it responds to the initial perturbation of your states, and there's also discriminative approach trying to directly distinguish the distribution, probability distribution between area law and volume law phase of the measurement outcomes. So I think our approach kind of is like a combination of these two. We try to use a generative approach to learn the distribution, and then we do not look at the initial state kind of perturbation, but maybe that's not important. Anyway, let me summarize. So the quantum measurement outcome serves as this quantum language nature tries to speak to us, and the quantum device capable of collecting them, so we should maybe learn from them. And then the question whether LLM can learn to speak this language, sometimes it's yes inside the learnable phase, and that helps us to overcome post-selection problem, and then we can probably build data-driven decoders for maybe quantum error correction task. But sometimes we must also notice that there's also limitations, and this limitation is fundamental. It is not possible for classical machine to learn everything about quantum device. So there should be learnability or decodability transitions. And even starting those transitions are very interesting. So thanks for your attention. Yeah, that's it.
Questions? Yeah, please.
Yeah. Thanks for a very nice talk. I just want to make sure I understand correctly. So the reason why the machine learning training model can perform better in some cases than the gate-based simulation is because the training data is using noisy data from device.
Yes.
Does that mean this approach is device dependent? Like if you train it on like a certain system and then apply it in the system with different noise model,
I think it's very good to be device dependent. It's very, you definitely want to train your decoder based on the specific device. Each device has its own noise model, which is very hard to infer a priori. Yeah.
Maybe, follow up on that. So is there a sense in which, like, do we know, like, necessarily if there is or is not, like, an efficient algorithm, like, without using machine learning? Like, for example, I might naively imagine that I might attempt to first learn the noise model and then I just simulate it.
Yeah, it's not about algorithm, because efficiently simulable doesn't mean you can efficiently learn. Learning is agnostic to the underlying algorithm you're trying to perform. So this is a direct end-to-end approach. So even if I tell you what kind of gate I'm performing and then what kind of operation, you can try to maybe build a simulator and improve your simulator. Maybe you have efficient simulation. But eventually, we wish to develop data-driven approach, which directly learn from data.
Okay, so maybe my question is kind of naive without knowing how this actually works. Like, can I attempt to understand what is happening under the hood as like the machine learning model is trying to learn some properties, certain properties, for example, noise model of the system? Or are you saying that that's just not
learning also the noise model, because the noise probability distribution will affect, will deform your measurement outcome distribution. What the machine learning directly learns is the measurement outcome distribution. It's only responsible to whatever measurement outcome data collected from the device, and just try to learn to build a model to model its joint distribution.
Okay, so you're saying like I shouldn't just try to interpret what
yeah, you shouldn't try to open up this black box and see which part is the noise model, which part is the circuit, which part is the gate. No, the machine doesn't even know all these concepts. It just learned the measurement outcome distribution.
Okay, fair enough. Yeah. And also, like for your last comment, like about this learnability transition, like is that something that one can prove that you can never use AI to solve this? Like,
Matteo has a paper, and then but I think it's still we have the understanding is still limited. There There's some argument about sample complexity from the learning perspective. But I think what kind of essential feature in this joint probability distribution that prevents us from efficient learning that is still missing?
Sorry, so the learning, those learnability proofs are also applicable to machine learning approaches?
Yeah.
Okay.
Yeah, thanks for the interesting talk. I think my question is maybe a follow-up on the last one that was just asked, which is the first problem for kind of decoding or preparing the EPR pair. The solution, as you wrote down, ends up just being the parity of the even and the odd bits. And I guess learning parity with noise is one of the most fundamental, like, hard learning problems we base crypto systems on. So I was wondering if you could comment on the connection to that. I mean, I don't think you have to use this query model. You have more control, so you can probably avert this. But I was wondering what your thoughts were.
If you have, so it's not a generic learning parity with noise model. The check matrix is very definite, and then. And even with that, it's very challenging for machine to directly learn long parity check from data. So we need to actually have some tricks. So that's called curriculum learning. You first learn the data with very short depth, short length, and then that learns 2 parity check, 3 parity check, and so on. You just gradually learn all this in the learning process. So that's how.
Yeah. Is that what you did here?
Yeah.
That's what you did here?
Yeah, we need to mask our data with different kind of mask in order to train the machine. It's like when you try to learn physics, you go to a library which has elementary school book and primary school and middle school and university, right? And then you just put all the book in the library and the kid enters. And then when you start to learn, it will, of course, doesn't know what all this high level knowledge, but when you first learn about low level correlations in this parity check, it gradually develops representations for this parity check in its neural network, and that enables it to learn even higher correlations. Yeah.
Great, thanks.
Yeah.
Wenzhao? Okay, thank you. I just maybe also kind of follow up. Also, I just try to confirm I understand the first part of your talk. So the goal of the first part of your talk is not to avoid some post-selection problems. It's more like conditioned on the measurement, the stabilizer checker measurements, and with the real device has noise, how you correctly encode the original state.
I think the purpose there is a proof of concept, because you are preparing EPR state condition on this measurement outcome.
Sure.
If you don't know how to select based on this measurement outcome of your data, then you basically get a maximum mixed state, and then you don't have entanglement between A and B. So in order to discover the A and B condition on the measurement outcome, you really need to know how to classify your data. And then this classification, if I didn't told you that it's an EPR pair teleportation experiment, I just hand this data to you. You really need to rely on a learning approach to uncover that there are actually 4 different class of states, and then they should be classified by certain rules.
I see. So for example, can the algorithm tell, I don't know, let's say you have a target code or surface code, they are kind of very similar, but still different. Can the code distinguish these two?
Yeah, I think the more useful kind of problem is if you have all the syndrome measurement outcomes, which classify into different logical arrow sectors. Yeah. And then it's also a classification problem. Just classify what are the logical states conditioned on the syndrome measurements. Yeah. So you can use this data-driven approach to learn that. After learning, you will have a decoder for your quantum error correction code.
I see. Thanks.
Yeah.
And at least for simulation, it seems in general to require exponential classical resources to overcome it.
Yeah.
I guess it relates to the previous question. So do you see this like fundamentally that to overcome post-selection you need something there?
Yeah, I think so. So there are easy cases where you can learn efficiently. Then that learned algorithm is an efficient classical simulator as well. So, but there are also hard cases where you cannot learn efficiently. But whether or not you can come up with other simulator, that's a different problem, right? Yeah. So I think if there's a very difficult case which you can prove there's no classical algorithm that can simulate in any sense, then learning will also fail in those cases, right? Because learning is also a classical, it's just a variational classical simulation algorithm. Yeah. Yeah.
Is that true? Because maybe you just didn't find a good classical.
I mean, maybe there can be proof that in any cases, there's no, this classical, there's a gap between classical simulable and quantum simulable, right?
I guess the question is also related to some of the previous questions. The EPR case, where your full selection with simple, do you really need the transformer?
Yeah, yeah, we don't. So that's why it's a proof of concept kind of first experiment to check that everything works, right? Yeah.
Hey, may I ask a question? Because I don't know much about large language models, but I would imagine that they have some kind of geometry in that architecture, in that language is a 1D problem, right? One word followed by the other. Is this something, like, is this true? And also, is it something that matters here? For example, when you have to...
But for this nowadays, this transformer model, attention is all to all, so there's no geometric locality. So anyway, so doesn't matter. Geometry doesn't matter here.
Okay, so there's it doesn't matter at all what the
And it's actually a nice thing.
is.
If you build your neural network on an all-to-all base graph, then you can let the network itself to find which token is more important to attend in order to make the final prediction, right? So instead of humans sit there and try to come up with a very good post-selection scheme, it's essentially machine emergent automatically from data. It learns a post-selection scheme. It's like that.
Thank you. If there are no further questions, let's thank our speaker again and all the speakers of this session.